Okay, so with that, we're going to get back on schedule and on track. Haltvick with Minnesota DOT. There's Nick. We're going to go through a pile bent strengthening of an in-service bridge.
Good afternoon, Nick Haltvick. So I'm with MnDOT. Similar to Sarah, I'm the North Region Bridge Construction Engineer, and the reason I introduced my title is I'm a jack of all trades, master of absolutely none of them, and fits in really well with this pile strengthening because not only do I work on specifying some of the design criteria for when we build new bridges, but I also get involved with a lot of the rehab work, and so I truly see the full life of a pile, which ends up being a good fit for this particular project. So today I just want to talk a little bit about where Minnesota is trying to move with this type of substructure for us. It does tend to be one of our more bread and butter structures, not only with previous builds, but also moving into the future. And we do recognize that it has a very significant Achilles heel that we need to try to get on top of. Minnesota primarily drives all of our pile, and we're using generally about 80% CIP, so a steel shell that we later fill with unreinforced concrete, or we're using H-pile, primarily for all of our foundations in the state. And so our contractors are very familiar with this. We have a large inventory of diesel hammers to install this work. So again, it becomes a very cost-effective solution for us with new builds. Just getting some more terminology. So on the left here, we have the open pile bent system. That's more what I'm going to be focusing on today. In some instances, some of our district partners consider this accelerated bridge construction, again, for new construction because you eliminate the need for a cofferdam. You eliminate some of those access challenges and really diminish some of the environmental concerns that we have during construction. Also poses a challenge, obviously, for an in-service structure in seeing enhanced levels of deterioration. We do construct some closed pile bents. Generally in new construction, we're looking at this in areas that are known to have heavy debris flows during flooding or heavy ice loads during the spring runoff. So again, though, the trend is to try to create that open pile bent for a more cost-effective solution. So just a few numbers, as Sarah alluded to, there's about 21,000 bridges in the state. If you just narrow it down to span bridges that would have this sort of configuration, we're at about 8,700. And of this, about a quarter of them have these pile bent piers on there. So it's no small quantity that we're trying to deal with at this point. So let's get into what we're starting to find with these different elements. So in our bridge field inspector's manual, we have some of the different characteristics that we're asking the inspection folks to go out and capture when we're looking at this type of substructure. And I know it's difficult to see, but it doesn't take much for piles in this configuration to get into a CS4 type condition. Really, we're just saying once it exceeds 10% of the total cross section. Now, because if you look specifically at our cast in place piles with the steel shells, they're unreinforced. And so that 10% can make a big difference in your load carrying capacity. Oftentimes it doesn't, but nonetheless we want to know about it so that we can hopefully become more proactive in retrofitting and maintaining these structures. And so just to look at our data, and this slide is a bit old now, but nonetheless, I think it still rings true. 1 out of 10 bridges that we have in the state with pile bent piers have at least one pile with CS3 or CS4 condition in it. So again, we're starting to need to tackle this. And quite honestly, I'm going to tell you, after the drought we had this summer, I expect this number to increase. And you'll see some photos why as we move along. So like most of the country, we were in a fairly severe drought this summer. And so this is a picture of one of the bridges we looked at in particular. You can see the normal water line in this case is about 3 or 4 feet lower than what we typically would inspect. Now for these pile bents, they generally do not fall within our normal underwater inspection cycle. So oftentimes they're not getting looked at with the same lens as some of our more major river crossings. And so oftentimes, and it pains me to say this, a lot of these piles, we've seen this 3 feet for the first time since that pile got knocked into the ground in the 60s. Right, so that can be kind of problematic, especially as we're trying to plan projects and plan our maintenance. And so, again, this does still have some limitations. Primarily, we're using boats or waders to get out there and try to look at these. But certainly, unless you're doing an underwater inspection, you got a guy reaching down, trying to feel with his hand, do we feel pitting here? I mean, certainly if you have good water quality, there's a potential that you can take some measurements, but it's difficult to say the least. And so the low water level, while it was wreaking havoc for a lot of the agriculture, it worked out okay for our inspection program this summer. It made for a busy summer as well. So what did we find? And I'm going to show you some examples of not only what we found, but how we're trying to address this and hopefully plan for it in the future. So the photo on the left was from a bridge where the DNR had lowered this artificial lake that was just upstream from the Mississippi River to do a project. So crews got out there with a boat and started scraping off this marine gunk, loon poop, whatever you want to call it, right? And from the surface, it didn't seem so bad until we started taking our D reading measurements. And we found that in this particular picture right here, that's almost 70% section loss to that steel casing that was existing. Again, first time we'd seen this since it got knocked into the ground. Photo on the right, this was another one where the water was way down in the Moosehorn River up in our northeast district. Notably about this one, so we had a contract paint project in 2018 where you can see the red paint, and that's how high the water was during that project. So now you get back down, you can see the original paint system from this bridge that was built in the 60s to, again, now even lower if you look at the bottom of the screen. Hopefully the color's bright enough, but we have some significant pitting, and I'm going to talk a little bit more about this bridge later on. A lot of different findings like this were coming in this summer, again, making for a busy summer. The weather does get a little chilly in Minnesota, so we do inspection from the ice. So this is a picture from March when we had some low water levels. This is on a bridge that's just adjacent to the Canadian border where we went out, we chiseled through the ice, knowing that there was already some issues on this one, to prep the surface so that once the temperatures warmed up a little bit more, we could actually paint this pile. So we do some winter maintenance as best we can as the conditions allow. And certainly we've been finding issues with cracks in our welded seams. And so the picture on the right here is from a pile that I believe was installed in the 70s, and the picture is kind of tough to see, but at the very bottom is where we believe the crack likely initiated during driving, and this crack has continued to grow with freeze-thaw cycles throughout the years. Fortunately, this is located directly beneath a barrier, and I think there's about 17 piles on this bend. So this one we're just going to continue to monitor at this point, but we do catch these problems from time to time too. Minnesota's had generally poor experience with field welding, so this is not an easy fix for us, which is in this case why we're monitoring. And we don't always just have problems with piling in the water. And so the photo on the left here was a picture from a bridge in Duluth, Minnesota, up on the tip of Lake Superior, where this was just over poor soil. You can see the moist part of the H pile there. That's where the soil was in its as constructed condition. We happened to find through a routine inspection some of these pile, and this isn't even the worst one, with over 90% section loss. So I remember this very vividly. It was their first Thanksgiving for my first child. I got called in the office to do this emergency repair for the district. So it's a very vivid one in my mind. But that was just over poor soil with poor surface drainage. Again, picture on the right, very similar situation again. So we're trying to deal with these things and try to not let it get to this point, because obviously this is you close the highway down, right? And that's a big deal. So we've equipped our inspectors not only with better tools, D-meters, things like that, to take the measurements, but the measurements also have to have some meaning to it. And so we've provided some of these spreadsheet tools where they can go and try to quantify how much section loss is there before they even give the bridge office, our central bridge office, a call. And so in this case, we've instructed to take approximately 8 readings around the circumference of the pile, and it'll compute a worst case scenario section loss, which is useful, but you got to kind of take it with a grain of salt, right? Depending on where along the length of the pile this occurs. So we do want to try to quantify this as best we can. And so oftentimes we'll take more detailed measurements. And so this is from that photo a few slides back where we had the severe pitting at the water line. And this inspector had basically determined what the equivalent circumference was of the pitting versus the equivalent circumference of the rest of the area that just had section loss, right? And so that weighted percentage ends up being 83%. And the reason I show these different examples is these tools have become very useful for us to try to get away from that knee-jerk reaction and try to provide more meaningful feedback quicker. Because it used to be they'd call up and say, "Hey, Nick, we've got a couple pits on this pile." "Oh, okay. You send me a picture?" "No, that's more than a couple pits, guys. Like, let's get some measurements on this," right? Or, and some of them would be like, "Hey, this bridge is going to fall down." They send you a picture. It's like, "Well, no, just scrape the rust off. We're okay," right? So this data-driven approach has really helped expedite these analyses to make sure that we're making the proper calls at the right time, whether it's restrict traffic, emergency repair, or, hey, just plan something for the future. So I'm going to give 3 examples of what we've looked at and tried for strengthening. And again, these are mostly pictures from recent. In fact, the one I'll highlight was just completed here about a month ago. First one, this is Bridge 9462 near St. Cloud, Minnesota. This is that pile where the DNR had artificially lowered the lake, and so the water's pretty stagnant through here. It's green, it's stinky. There's got to be something more than just that wet-dry cycle that's driving this corrosion here. But nonetheless, the water is also at about 10 foot deep, so access is difficult, to say the least, for a good thorough inspection, let alone doing some sort of strengthening. So little details about the bridge. It was constructed in 1962. Originally, the pile was protected with a paint system that contained a lead primer. This bridge was widened in the 1980s, and we had a few additional piles installed to support that widening. But otherwise, they just tried to recoat the piling as best they could at that point. So we know that the upper portion, the lead would have been removed at that time. But anything below that, we still are going to have to deal with the lead paint chips, if they even exist anymore. I would suggest not, based on the level of corrosion. But nonetheless, it was one of the environmental things that we had to address with this project. Uniform section loss in this case, and the bridge happened to be a continuous concrete slab span. Upon finding this, we were able to get by with just managing it with permit load restrictions. We didn't have to post a bridge or do any special lane closures or anything along that nature. And we decided that based on the structure type and the ability to share loads between the piling, we could simply preserve the original condition. And so what we're doing here, and we got research money to try out this method, is we're installing a stay-in-place fiberglass form that'll be pumped full of a grout material from 2 different vendors we're going to try out. And we're actually going to have a diver do this work. That was the advantage of the research project, is that what typically would be very cost prohibitive for our folks to go out and do, we can do under a negotiated maintenance contract using this research dollars to try something new so that we can assess this tool in our toolbox. So again, we're going to pump in this grout. We're supplementing with some reinforcement due to the level of section loss that was observed. And so the 2 products that we're going to be trying, we have a 5-star, this Pile Form F system, where the diver is going to go down, hook up to the tube, and pump it back full of grout. The second system we're going to try out here is a Simpson Strong Tie FX70 system. The advantage with this one that we see is generally you can pour this in from the top. So this is much more geared towards our maintenance folks being able to go out and perform this repair as more of a preventative style instead of a strengthening. So we'll be trying both of these out because of a lot of permitting issues. This unfortunately didn't get going this season, and we're looking at doing it in May of next year when the ice breaks and we can get the divers in there more cost effectively. So excited about this one. I know Wisconsin did a really big pilot project, and that's where we borrowed a lot of this information from to lead us to these decisions for this pilot project for us. So again, that'll be going next year. Example number 2, this is the picture of those deeply pitted piles, the Moosehorn River on I-35, so just south of Duluth. This, again, kind of a slow-moving river, but a much wider crossing than what we were dealing with. Typical water depth in this area, I think, on a normal season is about 6 foot. Rob's telling me 4 maybe. So the water was down. Nonetheless, our crews were able to go out there, and this one happened to be found. We were planning on going out and painting this area that we knew got missed with the contract project. And so Rob's crews were out there. I say Rob, he's the district engineer up there, so he was heavily involved with this one. They were planning on painting these piles when they noticed how much pitting was going on. So we went out and grabbed those measurements and realized, yeah, we got a big problem here. So bridges were originally constructed in 1968, again protected with a paint system that had a lead-based primer. Painted them. Of course, we didn't get far enough down with that 2018 project. But when we went out and looked at these ones this summer, we saw some of these piles happen to be cracked all the way through and with very significant pitting. Continuous steel beams here, so a little bit of load sharing back and forth. Minnesota primarily uses pre-stressed concrete beams in a simple span form. So when we see these problems, we do like to see that continuity to give us maybe a little bit better feeling on what's going on. But unfortunately, and the picture maybe doesn't do it justice, but if you look above where that wet zone is, you can see there's a crack there. You can see that we've lost some aggregate through that opening. And this is carrying interstate traffic. I was fortunate enough to be on my way up to vacation, so I got to take a conference call on this one from the end of a dock. I wasn't fishing during, I promise. It was all work related. But nonetheless, we were able to get the interstate reduced down to 1 lane in the matter of hours. And the bridge crew was able to get out there, and within days we had everything opened back up with a temporary fix obviously with some permit load restrictions back on. And so our bridge crews were able to procure some oversized pile, bend it into shape, and put in these steel collars. And this was basically just to address that crack all the way through, so that if we would have had a high lateral load event, that pile wasn't going to slip off the top, right? I mean, we had to acknowledge that this didn't happen overnight. Certainly we've been driving on this for a long time, but we couldn't keep 35 closed as long as we necessarily needed to, just on a feel-good scenario, right? So we installed this temporary measure while we worked through the permitting process to get a more permanent fix. And this went on really well. I was really impressed with the crew's ability to just get this done and get it done quickly. So this permanent fix in this case, because we had lost so much lateral capacity, we elected to go with concrete infill walls using self-consolidating concrete. And so with this, the crews were able to roll in a temporary dewatering system because of the depth of the water in most cases was 2 to 3 feet due to the low water level. We were able to dewater, and because these were twin bridges, we were able to take care of 2 piers at once with one mob, which worked out pretty slick. Rented some smaller equipment to do the excavation to get down to a certain embedment where we actually had good, competent piling again. Form it up. Rented the form system from an outfit out of St. Paul that could handle the SCC pressures, and then we were able to pump these things into place, strip the forms, and finish it up. And so, Rob, correct me if I'm wrong, it took him about a month from start to finish to do the actual construction work, right? Right. So obviously temperatures are falling in Minnesota, so not maybe the best time, but certainly it was better than when we left, right? So really impressed with the crew. I mean, this worked out really well for us. Obviously not necessarily the situation we want to get ourselves in, but a good reactive repair that we know that our folks can very easily accomplish. Probably the biggest hurdle with this one was the permitting process. I think, 500 mussels they had to relocate before we could do any of this work. Does that sound about right? 900, excuse me. So, I mean, just getting through the environmental portion of it was a challenge. Yeah, it was a DNR thing. So, yep, the mussels in this case took precedence over the traveling public. So, I say that tongue in cheek, excuse me. So the last example, so this is Bridge 27925. So again, interstate westbound over Shingle Creek. This is right in Minneapolis, kind of a lazy creek that runs through Minneapolis. I wasn't as involved with this project, but this is an example of where we'd like to try to take more of our preventative measures at. And so again, a continuous slab span bridge constructed in 1964. No other major projects, if you will, on it since its existence. So surface rust is observed at the water line, and this was one where we know replacement is going to be difficult, to say the least. And so getting in here preventatively to try to extend the service life of this structure was going to be a big improvement for it. And so in this case, we were looking at more of a pile wrap solution. And just looking at banding mostly that wet dry zone, because it was the belief that that's what's primarily pushing all the degradation at this area. You can see on the left here, you got a picture of the pre-wrapped condition. Obviously some deterioration, the paint loss, but you got that good orange primer on there, right? That lead seems to hold forever. So we do know that the degradation isn't as severe as some of the other locations. But in this case, they weren't able to fully cofferdam and provide a nice dry condition to work in. So contractor went out there, installed some of these barriers to modify the flow rate, and were able to put in, on the slide on the right here, these little boxes that they could then jump into like a mini cofferdam and perform the work from. And so you can see, not a huge bridge, but access still was a bit of a challenge, right? You're not walking out to these piles. You're using boats, you're using a little floating raft. So this little system that they were able to build around the piles, you could go down, dewater it, and then you could put a guy down in there to do the surface prep and ultimately put the wrap on. And so in this case, this was a Denso product, Denso Sea Shield 2000 HD. So pretty successful project. Our goal would be to monitor this long term and hopefully get a skill set built up so that more of our bridge crews could perhaps perform this level of maintenance too, certainly within their skill set. The planning piece of it, right? So we've made a very cognizant effort over the last 10 years to really enhance our inspection data, and we've made some tremendous gains in it, which is good. Now, as Sarah alluded to, we really need to start leveraging that to our advantage and trying to plan for some of these. So instead of me standing up here saying 1 in 10 of our bridges have this CS3 or CS4 condition, but we don't necessarily know what we're going to do with it, we're going to try to get more proactive on it. And not only are we going to continue to inspect, but we are going to, in some cases, schedule underwater inspections on these to make sure we really know what we have in these zones that we haven't previously been able to see. And really the key takeaway is we want to establish good, competent baseline measurements so that we can predict what this deterioration may be and make sure we're not getting into scenarios where we have these deep, deep pits that are really hard to handle, right? And so again, I'm showing kind of this draft concept of what we're thinking, but really the idea is once you identify you're in CS3 or CS4, the goal would be to enter into more of a flow chart like structure to start the conversation. And so perhaps if it's less than 25% section loss, crew, you can pick from these 3 or 4 standardized details, right? And just let us know that you're doing it and if you need support, right? If you're kind of in that middle zone of 50 to 25%, well, we probably need some analysis to figure out, well, how critical is this at this point? And again, hopefully we can have you A, pick off this shelf, or B, plan maybe a bigger district-wide contract to go out and have a contractor hit these in more of like an IDIQ format. And then obviously for the over 50% section loss, that's almost going to be by default analysis, and let's figure out what your skill set is to address this or get a contract in place. So again, this is really draft. I mean, we spent the majority of the summer just reacting to a lot of this, but this is the route we'd want to go for our in-service structures. Now, again, acknowledging that we have this issue, we don't want to continue to perpetuate it, but yet we still want to build this type of substructure where we can. And so we are looking at doing more enhanced soil testing to try to identify if the soils in the area are more conducive to causing advanced section loss. So most of these tests we can do in-house, which is why they've been selected so far. And certainly we're leaning on the local knowledge. You know, if we know that we're already having problems there, maybe despite what these tests say, we're going to take some of these mitigation measures up front, recognizing that the life cycle cost is much cheaper. You know, again, this flow chart on the right that I made very purposefully small because it is in a draft form. This is more looking at how are we going to get to that testing criteria and when does it make sense to do it? Because certainly the testing has a cost, right? And we don't need to just frivolously test all these soil characteristics if there's not a real need for it, right? And so trying to take this two-prong approach of both taking care of the in-service and recognizing that we really want to make these structures last 75 to 100 years with our new build. And so again, some of the mitigation measures that we're trying to roll into more of our standard operating procedure are adding sacrificial thickness when it makes sense. I mean, certainly for small jobs, you know, single bridges out in the middle of nowhere, this is probably a good option, right? Because you don't have the risk of pile overrun by predicting your driven lengths incorrectly or things like that. A little harder though for things like an H-pile, right? You can't just say, oh, let's make my H-pile a 1/4 inch thicker, right? I mean, that's got a little bit different consequence to it. So we're also trying to look at what are some assumed loss of sections that we could build in for an analysis to try to back calculate it in. Now, that works pretty well for uniform section loss, but as you see, that's not what we always deal with, right? We get that severe pitting that's much harder to handle and model. Certainly one of the options we're looking at is removing corrosive soils where possible and where cost efficient. Project I'm involved with in Duluth right now, I can tell you it is not cheap to remove corrosive soils either. And so you have to kind of balance that out with the overall project needs and the environmental process. And then finally, coatings. And so we've been using galvanized pile in these applications for about 20 years. And it is a tool in our toolbox. But what I will say about galvanizing, and this picture shows it absolutely tremendously. We only need galvanizing within the first 5 feet of what this bottom of footing elevation is supposed to be for this particular picture right here. And we're stopping these piles in a really dense layer of sand that is very irregular. And so those 2 piles that are right there are at about 130% of what we need for foundation bearing. But do we have any of our galvanized stick in the ground yet? So our corrosion measure failed right here, right? And this is very difficult to predict, right? When you got a little 4-inch boring trying to pick out what's going to happen in this 50-foot by 50-foot footing, right? So just a little bit more background because this consumed all my Christmas last year. Those 2 piles hung up at 55 foot. The piles that are on the back side of this, we never found foundation bearing in 140 feet. So that's how irregular this site is. So try to plan corrosion mitigations. It's quite challenging, to say the least. So again, multiple tools in our toolbox is what we're looking at. So I know I went through that pretty quickly. I'm certainly entertain any questions, or feel free to shoot me an email. Yeah, go ahead. So the question was regarding H-piles were showing up in some of the slides, and what are some of our considerations moving forward? Hopefully I truncated that correctly. So H-piles, we will still use those, but typically we reserve those for when we're going to encase the entire system with an infill wall. And generally, we're specifying those for when we know we're going to have rough driving conditions. And so those as an open bent concept I'm not going to say have been completely eliminated, but they're much less desirable for us on new construction. As far as the new section goes, we have done a few precast concrete piles. Our state and our contractors aren't geared up very well for them, so I don't see us moving away from the steel shells anytime soon. And that's where we're really starting to look for more of those mitigation measures. And one that I left off too was starting to throw a rebar cage down there. Primarily we're driving 12-inch, 16-inch diameter, which becomes somewhat problematic. Not the end of the world to get concrete in, but more projects now, a couple that I've worked on recently, we're using 30-inch, 36-inch diameter, which is more typical of a cast-in-place column, right? So our contractors are easily able to get the reinforcement down there and provide that extra layer. All right, so the question was about sacrificial anodes in these piling systems. We haven't, at least to my knowledge, we haven't done a lot to date with that on our piling. We're certainly starting to look at it on more of our cast-in-place structures and our pre-stressed beams, but quite honestly, part of the hurdle has been just the pure cost and the contractor learning curve. But no, we are definitely starting to look into that. Yeah, so the comment was talking about when we do encase these pure structures, obviously changes the scour characteristics. And so MnDOT, we don't really have a standard bridge design. We skew it at whatever you need. I've seen a plan come across my desk instead of, I think the river was coming through at 89 degrees instead of 90, right? So we built it at 89. So we do try to mitigate it that way. But to your point, it does cause different scour issues. And that's where we play the game of, can we space our piling enough so that we don't have an ice load issue to allow for that open bend system? And sometimes that's just not possible, especially with the ice flows we see.
Thank you. Thank you. That was great.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.